This video covers uniform charge distributions. In this example, we have a conducting hoop with a charge Q and a radius R, and we're asked to determine the electric field at the hoop's center. Well, here we don't need to do any math, because a charge over here is going to have an electric field that goes out this way. And this charge is going to have an equal electric field that goes out in the opposite direction. So these two will cancel out. And that's going to happen for every single charge along this hoop. So our electric field at the center is equal to 0. In this example, we're looking at the same conducting hoop with a charge Q and radius R, but now we're asked to solve for the electric potential at the hoop's center. Remember that electric potential is V equals KQ over R, but this is true for only point charges. So we need to solve for the potential of every individual point charge along this hoop. But because it's a scalar, all the Q's are located a distance R away from the center. So if we sum up all the Q's, we're simply going to get the total charge on the hoop over the total distance, where R is equal to capital R. So our potential is simply V equals KQ over R. So here's where it gets a little trickier. Here we have a point P that is located at a distance x to the right of the center of a hoop with a charge Q and a radius R. We're asked to determine the electric field at point P in terms of R, X, and Q. So what we're going to do is we're going to be using our electric field equation, which is KQ over R squared, but we need to apply it to a uniform charge distribution. So what we're going to do is we're going to divide the hoop into elements of charge dq. So we're going to look at infinitely many little dq's. Now, each element of charge creates an element of the electric field. So if I were to look at just this little dq, it creates an electric field that goes out in this direction. So all the dE's point away from the positive dq. Had dq been negative, all formulas and values that follow would have been the same, but the only difference would have been that it's opposite in direction. So this equation now looks like K dq over R squared equals dE. Now, for every single dq, there is another dq on the opposite side of the hoop. What that means is if I were to look at another little dq over here, it would create another electric field portion in this direction. And that would be true for every single dq. So what that means is because we have vectors here, we need to look at the components instead. So we have a component of the electric field in the x direction and a component of the electric field in the y direction. That's true for this top one, and that's true for the bottom one. Now what you should notice here is that these portions of the electric field are going opposite in direction, and they're going to be the same magnitude, which means they're going to cancel each other out. So all we're going to have left is an electric field at point P that goes out in the positive x direction. So all we're going to need to focus our efforts on is solving for the electric field in the x direction. So again, dE equals K dq over R squared. Again, this is the magnitude of the electric field produced by this 1 point charge. But now we're only going to be looking at the x component of this electric field. So if we want only the x, we want to make sure that we add cosine theta, so we can solve for only the x direction. Again, this equation is now the electric field due to a portion of the total charge. So all we need to do is add up all the little portions of the electric field to find our total. So if you look at this equation, on the left-hand side, we're going to get our electric field in the x direction. On the right-hand side, k is a constant, r is a constant, and theta is a constant for all dq's at all points along this hoop. So that means I can take them out of my integral symbol. And I'm left with just dq. Well, our total charge q is equal to all the sums of our dq. So that means I can just replace, when I take the integral of dq, it is just q. But our problem said that we had to leave it in terms of r, x, and q. So that means I need to replace little r with something that corresponds with capital R, and I need to replace cosine theta. Well, we know that if this creates a triangle here, then r squared is equal to x squared plus r squared. So I have x and r that I can leave in my final equation. So I'm going to replace r squared with x squared plus capital R squared. Now we need to get rid of cosine theta. We know that cosine theta is equal to adjacent over hypotenuse. So adjacent to my angle is x, and my hypotenuse is r. But again, we cannot leave r in my final equation. So I can actually replace r with the square root version of the equation I wrote earlier, which is x squared plus r squared. And instead of writing the square root, I'm going to write it as a 1/2. Remember that those are equivalent. So that means where I see my cosine theta, I'm going to replace it with x over x squared plus r squared 1/2. If we simplify that, remember here we have an invisible 2 over 2, or to the 1 power. So I can combine the bottom two to get k over x squared plus r squared to the 3 over 2. Remember, we have an x on top and a q. So this is my final answer for my electric field. A distance r away from a hoop. Again, looking at the same problem, we have a point P located at distance x to the right of the center of a hoop with a charge q and a radius r. Now we're asked to determine the electric potential at point P. Again, we are going to be using V equals K times the sum of the q's over r. But also remember that potential is not a vector. It is a scalar, meaning there are no components. So in this case, r is the same for every charge around the hoop. So if you add up all the individual charges, you will result in the total charge on the hoop. Again, V equals kq over r is our potential. But remember that little r cannot be used in our final equation. So we're going to use the same equation that we used earlier. Namely, x squared plus r squared is going to replace our little r. So here we have x squared plus r squared. And again, we're replacing r, not r squared. So we're going to write this to the 1/2 power. And this is our potential at point P, a distance r away from our hoop. In this example, we have a point P that is located at a distance x to the right of the center of an arc with a charge q and a radius r. You will need to include this in your notes for full credit. Here we're asked to determine the electric field at point P in terms of lambda, r, theta, and known constants. Again, you are going to be using the equation E equals kq over r squared, but you need to apply it to this particular situation. So, what that means is that a small charge dq produces a component of our electric field. So this dq is creating this dE of our electric field. If we were to look at another dq at some point on the other side of the arc, it would create an electric field that goes out in this direction. So very similar to our other example, these electric fields are vectors, and it's going to have a component in the x direction and in the y direction. And just in like our last example, these components in the y direction are actually going to cancel out because they're opposite in direction, but equal in magnitude. So that means that at point P, we're only going to have an electric field that goes outwards. And this is only the x component of the electric field produced. So, what that means, if I go back to my equation, I want to solve for only the x component, which means that my electric field I originally had, I only want to know about the x version, which is times cosine theta. So again, I'm going to add up all the electric field components in the x direction to find my total electric field. On the left-hand side, we're going to get my electric field in the x direction. On the right-hand side, k and r are both constants, so we can pull both of those out of the equation. But theta is no longer a constant as it was in the previous example. So what that means is that I have a dq here, and I have a theta that changes. So I need to change one of those so that we only integrate with respect to one variable. What that means is we are actually going to be replacing dq with something else that we should know, which is our linear charge density, which tells us that our linear charge density is our charge q evenly distributed over the entire length of my arc. Again, it is simply a ratio of the charge per unit length. So, lambda dl is going to take the place of dq. Well, you might say that we still haven't replaced anything, but you're going to see that we're going to be able to get rid of dl in just a second. So this becomes lambda dl. Again, lambda here is a constant, so I can actually pull that out of my integral. And I still need to find a way to relate dl and theta. Well, dl is simply the length of this arc, and we said in rotation that x is equal to r theta. In this case, dl is equal to r d theta. So now you can see that we're going to be able to get rid of dl and replace it with d theta. So wherever I see dl, I'm going to replace it with r d theta. And now I only have one variable that I need to integrate with respect to. Here, you can see that one of my r's is going to cancel out. And I'm left with cosine theta d theta. Again, this is a simple integral, so we just do the integral of cosine, which is sine, so that this comes out to be lambda k over r sine theta. Now my limits are going to be from this point all the way up until this point. Now, your theta, your limits can either be in radians or degrees, depending on whatever your calculator is set to. So, in this case, we're going to head and put it as, this is going to be my final limit, which is pi plus theta, or 180 plus theta. Again, because our arc is shaped in this direction, and my angle's always measured from 0, from here to here is 180 degrees. My arc consists of from here to here. So it's simply 180 plus theta is my, actually I'm going to put in radians. Pi plus theta is going to be my top limit, and my bottom limit will be 180, or pi minus theta. Again, either of the limits would work. And this is my electric field of an arc, which if you evaluate your integral, it looks like this final solution. Again, if you needed to put in your numbers, remember that lambda is really your total charge evenly distributed over the entire length. But it was also equal to dq over dl. And the reason that we can make them equal to each other is because it is simply a ratio. And the absolute last piece, that if we're looking at the same situation with the arc, and we're asked to now determine the electric potential at point P, well, here we don't have to worry about angles because, again, potential is a scalar. So we don't have to worry about components. All we need to do is add up all the charge, which is just Q, and they are all the same distance away from point P, which is R. So our potential is simply KQ over R.